Hi, I'm Sudeep and I'm back with a new episode of the series Structural Analysis with StatPro Connect Edition. In the last episode, we have discussed in details as to why do we need to model sectional properties and material properties as a part of our modeling effort. Now that we have the answer to the question, we would discuss one of the sectional properties in great details today, and that is the cross-sectional area. But before that, if you are new to this channel, please take a moment to hit the subscribe button and join us in this wonderful journey of learning structural analysis with StatPro.
So what is a cross-sectional area? Imagine taking an I-shaped beam like this. Now imagine that you take a knife and cut this beam vertically downwards along the line AA. This is called taking a cross-section at AA, or simply taking a section at AA. Now when you cut the beam along this line, the beam would be split into two halves along this line AA, and this particular plane depicted by the arrow sign, the area of this particular plane would be called the cross-sectional area. If you have a W14 by 873 American I section, or the wide flange section as you'd call it, that would typically have the dimensions as shown on the screen.
So how do you calculate a cross-sectional area? Well, the members made of concrete usually have a rectangular or a circular cross-section. So a rectangular section looks like this. So in case of a rectangular section, which is common in case of when the material is concrete, let us consider the width of the section as B and the depth of the section as D. Then the cross-sectional area of this particular section is given by, and we have studied this in our primary schools, what is the cross-sectional area of the rectangular section. So it is given by this width into this depth. So it would be B into D. So that's the cross-sectional area of a rectangular section. The other common type of cross-section, in case the material is concrete, is a circular cross-section. And generally we would find columns having this type of cross-section. Now, if this cross-section, this circular cross-section has a diameter D, then the cross-sectional area of the circular section is given by pi into D, which is the diameter, squared by 4. So this is the cross-sectional area of a circular cross-section. Now let us consider the cross-sectional area calculation for some common shapes that relates to steel cross-sections. So, or rather the material that we are considering now is steel, and the cross-sectional shapes that are available with the steel material. So one of this shape is an I shape, which you can see on the screen. And let us represent the I shapes, the dimensions of the I shapes, with the notations that are used in the STAD user table general sections. We will discuss more about user table general section as we proceed in the course, but for now let us consider the dimension representations that are being used there to represent the various dimensions of the I section. Now this part of an I section is called the top flange, okay? So the top rectangle, that is, and the width of the I flange in STAD user table general section is represented as BFF, okay, which sort of represents the breadth of the flange, and then the thickness of the top flange is represented as TFF. Okay. The total depth of the section, which is from the top of the top flange till the bottom of the bottom flange, is being represented as dWW. Then the thickness of this portion here, now this is called, see, this is the top flange. Okay, this is the top flange, and this is the web of the section. Okay, and so this would mean this section here. This rectangle here is called the web of the cross section, and the thickness of the web in stat terminology in terms of user table general section is given as TWW, which would mean the thickness of the web. And finally, the last portion is called the bottom flange. Okay, and this bottom flange is another rectangle, and the dimensions can be represented as, for the width of the bottom flange, we can represent that as BFF1, and the thickness can be represented as TFF1. Now, how do we calculate the area of this section? So the area of the cross section would be nothing but the summation of the cross sectional areas of all these simple rectangles, right? And we already know what the cross sectional area of the rectangle is. So the area of the top flange, the cross sectional area of the top flange would be equal to the width into the depth. So it would be BFF into TFF. What would be the cross-sectional area of this web here? Well, this is another rectangle. So it would be the depth of the web, which is the total depth minus the thickness of the top flange and the thickness of the bottom flange. So we'll have, this is the total depth minus thickness of the top flange minus thickness of the bottom flange. This would be the depth of this section, and what would be the width of this section would be the thickness of the web, which would be TWW, right? So this multiplied by this would give the cross-sectional area of this web. And finally, we have one more component of this particular section, which is the bottom flange. So let us find the cross-sectional area of the bottom flange. And this would be simply BFF1, which is the width of the bottom flange, multiplied by TFF1, which is the thickness of the bottom flange. So we have the cross-sectional area of all the three components of this particular section. So therefore, the cross-sectional area of the I section will be the summation of all of this. So that would be equal to, so let us write from here. So it would be the first term in the expression BFF into TFF, which is the cross-sectional area of the top flange. Then we have the second term, which would be now this was the depth. depth of the web multiplied by TW. So bracket close. And finally, the cross-sectional area of the bottom flange, which is so this expression here gives you the cross-sectional area of the I section. Now note that in most of the cases you'd have the width of the dimensions of the top flange and the dimension of the bottom flange exactly the same. So in that case, these terms would be the same. So in those cases, you could represent this equation. So these two would be similar terms. So it would be 2 into and then this would be so now one of the things that you have to understand is that the top and bottom are relative terms. Now in stat terminology, those relates with the local axis of the member. We haven't discussed the concept of local axis as yet, but we are coming to it. But the top and bottom in that case would be related to the local axis of the member. Okay, but we won't get into details into that. But for now, just remember that there is a top flange and a bottom flange, and that's purely a relative concept. So another type of sections that are available for steel material is the channel section, which looks like this. In this case, we are assuming that, or generally it so happens that the width of the flange for the top and the bottom flange of a channel section are exactly the same. Now these are called the flanges for a channel section. So these are the flanges, and this one is the web. Okay, now generally for a channel section, the width and the thickness are the same. So the cross-sectional area for a channel section would be calculated as, so this width of the flange into the thickness of the flange for the top flange. Now exactly the same dimension is here, right? So we multiply that by 2 like this, and the other component is the web. Now we have already taken the area of these parts, so only that remains is the area of this part, web, which is not shaded. So the depth then we have to consider would be the total depth minus the thickness of flanges of the channel at the top and the bottom. So we will have the width in this case is TW multiplied by this depth, which would be given by G minus 2 into TF. So this is the cross-sectional area of the channel section. The terminologies that I have used to indicate the section dimensions are actually StatPro's way of representing sectional dimensions for the user-defined steel sections. Now, we would discuss in the future videos about the user-defined sections, user-defined steel sections in StatPro. But one thing to note is that you do not actually need to calculate the sectional properties manually. Once you specify the sectional dimensions, for the user-defined steel sections, STAAD automatically calculates the sectional properties. Note that the cross-sectional areas of steel sections that would be rolled out of a factory, be it an I section or a channel section, will not exactly be the same as we had calculated using the rectangular components of the cross-section, because the sections that is rolled out of the factory doesn't exactly have rectangular section components. It has something called toe radius, it has something called a root radius, and there are other slopes in the section. If we use the rectangular approximation to calculate the cross-sectional areas of those sections, there would be a degree of error in the cross-sectional area calculations. But we do not really need to worry about the cross-sectional area calculation of the sections that comes out of the factory, because it would be a part of a standard database which would have all the sectional properties listed, including the cross-sectional area. So instead, the standard steel section databases are built in. So for all those sections that are rolled out of a factory, STAAD would use the section database to extract the cross-sectional areas. So you do not need to worry about calculating them. So I hope you have enjoyed the discussion today. And if you think the discussion has added value, please do hit the like button and do me a favor. And please do hit the bell icon for more notifications from the Structure and Series channel. See you in the next one. Till then,